Hello and welcome to the Berkeley Review Oxidation Reduction Electrochemical Cells Read Along. This is part 3 of chapter 4 in the General Chemistry book. My name is Todd Bennett. I'm the author of the book. Also taught this, as I mentioned in some of the previous videos you probably listened to. I've taught for a little over 25 years. I teach at Irvine location and the Westwood location for Berkeley Review. And I'm going to try to take this chapter or this portion of the chapter as I teach it in class, because this is one of those subjects that, for whatever reason, in general chemistry classes, whether it's at the end of a semester or a quarter, and professors have a tendency to rush, or just maybe it's just not a major focus with some of the other topics, just traditionally more enjoyable to a professor. I'm not sure why, but over the years, I've definitely noticed students come in less prepared for this section than most. Usually because it was rushed and not gone into detail in school. The unfortunate thing is the MCAT sees this as a major topic. This is one of those areas you really have to learn your details. But the good news, it can be seen in a very simplistic fashion. So again, this is designed for people who have the book open and are working along with it. So have your book open to page 159. We're going to go from page 159 through 163. It's only 5 pages. But these 5 pages are probably some of the highest yield or most important pages you'll deal with in the entire book, just in terms of what they like to ask. My goal, and this is a goal not just for this video, but whenever I teach, is to keep things as a simplified system as much as I can and have the rules apply universally. So even though I'm talking about electrochemical cells at the moment, the rules I'm giving will also apply to electrophoresis. They'll apply to electrochemical cells. They'll apply to electric circuits. They apply to everything. So they're universal electric rules. So hang on to those as we go through them. I'm going to reiterate them every chance I get. We're going to cover, again, pages 159 through 163. I'm going to do figures 4.3, 4.4, 4.6 through 4.8. I'm skipping figure 4.5 because that's going to end up in a different, it's going to end up as part of a question in a different read-along. And I'm doing examples 4.8 and 4.9, so galvanic and electrolytic cells. So I want to start with galvanic cells. Galvanic cells defined as a cell that's favorable, meaning it will release energy. We call it negative delta G. When it's a favorable reaction, it also has a positive E or electromotive force. Galvanic cells can also be referred to as voltaic cells. So if you see that word in homework, you see that word on a practice test from us or AAMC or wherever you may see it, know that galvanic and voltaic both mean energy releasing. So every electrochemical cell has to have an anode and a cathode, and they got to be connected. So the basics of this circuit, you'll notice a wire going from the anode metal and finishing at the cathode metal. That's a pathway for the electrons to traverse. But every electrochemical cell, every circuit has to be complete cyclic flow of charge. So when you did circuits, if you opened a switch and disconnected the full cyclic flow, the circuit stops. Same thing with electrochemical cell. If you only had the wire and didn't have the salt bridge, it couldn't run. You need the salt bridge to complete cyclic flow. So overall, electrons are going to move from the anode to the cathode, and that's going to accrue negative charge on the cathode to offset that negative charge. Anions are going to migrate through the salt bridge back from the cathode to the anode. So you ultimately going to show complete cyclic flow of charge in a clockwise fashion. I'm going to systematically, the rules, just to tell you what they're going to be, are going to be 2 of the things I just said. Electrons flow from the anode to the cathode. That's always going to be rule number 1 for every electrical system. Anions migrate to the anode. That's going to be the second rule. And the third rule ultimately is going to be cations migrating to the cathode to get reduced. So let's go ahead and start with electrons. By definition, oxidation occurs at the anode, so electrons are going to be lost from the anode. So you'll note oxan, electrons flow from anode to cathode. Let's quickly revisit the mnemonic from the start. Leo, the red cat, says Gur. Leo, lose electrons, oxidation. Gur, gain electrons, reduction. And red cat, reduction occurs at the cathode. So for reductions at the cathode, this tells us then oxidation is the anode, that's the oxan. And again, electrons will flow from the anode. So there are my electrons. I want to integrate a physics thought, and it's important. It's easy to study in tunnel vision on general chemistry when you're doing general chemistry, but nothing on the MCAT is ever a single science passage, a single science presentation. you have to be able to mix things together. Physics has to be done in conjunction with OChem, with bio, with GChem. GChem has to be done in conjunction with bio, with physics, with OChem. Things have to integrate together. So it's critical. So I'm going to go ahead and consider a few circuit rules. First, in series. So this is a giant series loop starting with electrons leaving the anode and finishing with chloride anions. That's what I'm going to ultimately show, but any anion coming back and finishing at the anode. So it's a cyclic flow of charge. That means it's one giant loop, so everything is in series. You'll recall from physics, in series, you have the same current. Current's the same at any point in a series circuit. So in this case, because all the electrons are in series, they often move in unison. So if you've ever been to a theme park, in class I always joke about going to Rodent Park, a nickname that I have for going to Disneyland. If you're in line there, getting on a ride, when the person at the front line steps up and gets on the ride, everybody else gets to move up one step. So everybody's moving in series with one another. So no point in the line is faster or slower than the other. You're in series. So each electron here, notice they're going to move in series. They all moved at the same rate from the anode towards the cathode. So the cathode starts building up this negative charge. The cations that are in solution then are going to be attracted to these electrons on the surface. So you'll notice the first part, electrons are flowing anode to cathode. Okay, so in solution, as mentioned, you're going to have some cations. The cations in solution, they're able to freely move, whereas electrons, they're bound to the wire. They can't go into the solution. So for the cations to pick up electrons, they must migrate to the surface of the cathode metal. So over time, the cathode starts to build up in mass and size because these metal cations start accruing on the surface. So that process is known as plating out. To offset this, we have to have negative charge migrating back towards the anode. So cations can't be by themselves in solution. There's also anions in there. Again, I've chosen chloride to be the anion. So whatever the initial metal was, it came as a salt with the metal cation and chloride anion. The chlorides now, to offset the building of negative charge on the right-hand side, will migrate back. And again, they are all in series. In fact, it's kind of an interesting thought when you consider the wire and the salt bridge are both in series. So the rate at which electrons are going to flow from the anode to the cathode must be exactly identical to the rate at which chlorides migrate through the salt bridge. So notice every chloride migrated at the same rate. If I did all of them at the same time, you would note that electrons and chlorides are migrating at the same rate. Electrons are going to go to the from the anode to the cathode at the same rate as the anions go back through the salt bridge to the anode. Again, I'm a big proponent of the rules. So I want to just make sure that all the rules are being followed. Electrons are going from anode to cathode. Anions are migrating back to anode. Cations are migrating to the cathode where they're going to get reduced. So the three rules. Electrons flow from anode to cathode. Anions migrate to the anode. Cations migrate to the cathode. Important to hang on these three, and I don't know how many times I've said it, but I'm going to say it a lot more. Major thing I want you to bring home from this read-along is electrons flowing from anode to cathode, anions migrating to anode, cations migrating to cathode. So let's go ahead and look at figure 4-4. So you'll notice I've removed some things or whited it out. We're going to look at everything one by one, but the generic picture here is where we finished on the last picture. Electrons flowing from anode to cathode, anions migrating back to the cathode. So let's first identify what electrochemical cells are. Electrons flow from anode to cathode, so if they're flowing away from the left electrode, that must be the anode. So oxidation occurs at the anode, so we're losing electrons from there. On the other side, electrons are flowing to the right electrode. Red cat, reduction occurs at the cathode. GR, gaining electrons is reduction. So again, the cathode is picking up electrons. So electrons are flowing from anode to cathode. To balance out charges, again, anions have to migrate back to the anode. I want to look at the reactions. In this particular case, the anode, as I mentioned, is going to get smaller over time because the metal that's getting oxidized is turning into a cation. Cations can then dissolve in solution. So the anode starts dissolving away over the course of the reaction. On the other side, the cathode, again, the cations have to go to the surface of the metal to find the electrons. When they find them, they'll plate out on the surface. It's said to plate out. So if you've ever heard the term of electroplated material, that is because you use electrochemistry to plate out a thin layer of metal onto the surface of another conducting medium. So in this case, if it's a copper electrode and I'm plating out copper on it, it's just going to be a thicker piece of copper. So over time, the cathode grows, the anode diminishes. The other aspect is also want to focus on electrons flow from anode to cathode, anions migrate to the anode. So 4 parts: oxidation to anode, reduction to cathode, electrons flow anode to cathode, anions migrate back to the anode, so anions migrate to the anode, and then overall cations get reduced, so cations migrate to the cathode. So figure 4.6 or 4-6, this is the same thing but now specifically applied to a reaction that's very common in GChem. So I'm going to start with copper chloride in one electrochemical or one electrode, and then the zinc chloride in the others. So we typically draw anode on the left, cathode on the right. This is convention. Be careful because they don't always follow convention, but as labeled, anode on the left, cathode on the right in this example. Electrons are in fact flowing from anode to cathode, check. Anions are migrating back to the anode. The chloride again in this case is the anion, so anions go in the anode, check. And then ultimately, copper is going to get reduced, so it's going to migrate to the copper cathode. So copper 2 plus will migrate to the cathode. Cations will go to the cathode. So zinc, if you recall or look at the table of electrochemical potentials, its reduction is negative 0.76. In this case, it's being oxidized, so we're going to list it as a positive 0.76. Copper, you read from the table, is positive 0.34, so we just take it straight as it is. The sum of the electrochemical, or the 2 half-cell voltages, is the overall electrochemical cells voltage, so it's going to be 1.1. So we're going to get 1.1 volts from this reaction. Very common number. You probably have seen it enough times that maybe it's starting to sound familiar. We just want to make sure all the rules are followed. Electrons are flowing anode to cathode, anions going back to the anode, cations are going to the cathode to get reduced. So let's consider a question based on that picture we just saw, 4-6. We have the same cell, zinc metal. This time it's in a specific molarity, 0.1 molar zinc 2 plus, and then copper on the other side is copper metal and copper 0.1 molar 2 plus. So if you have your book open and you can see figure 4-6, it's the same picture. Wire connects them, plates, salt bridge connects the solution, so everything's set as normal. And they're asking what happens over time to this electrochemical cell. So first off, let's follow the rules. Electrons flow from anode to cathode, so they could ask questions about the electron flow rate, the plating out rate, some sort of current related question. They didn't, so that rule didn't help us much. Second rule, anions migrate to the anode. Again, there's no anions listed in this, they're not asking about it, but cations migrate to the cathode. That's the rule we care about. So again, the electrons, when they flow from the anode to the cathode, going to cause reduction. That means the cations are going to go and get reduced. So at the cathode, you have copper 2 plus in this case, migrating the surface, building up, and plating out. So the cathode gets larger, it plates out. Meanwhile, the zinc is giving up electrons. Zinc metal is going to zinc 2 plus. It's going to get reduced, or get turned into an ion. That ion is going to go in solution. When it does, its size is going to get smaller. It's going to get dissolved away. So over time, we know that oxidation is going to dissolve away your anode. So zinc metal definitely is getting dissolved away. I put a circle there picking the answer for now, but I could have made a tactical mistake. So I went, and that's right, I'm kind of jumping the gun. I haven't looked at the other answer choices. Have to be really careful to do this. Sometimes there's 2 right answers, one is better than the other. So let's go ahead and consider the rest. Copper metal is not dissolving away. Copper metal is getting reduced, or copper cation, excuse me, is getting reduced into a metal. So B is out. Subsequently, that also means that C is out because copper is getting reduced. So choice D, that I don't want to call it a throwaway answer, but the answer that isn't really in step with the rest. Zinc cation is definitely being formed, so that's looking true so far. However, precipitation doesn't mean it precipitates out as a pure metal. It's still a cation. Cations precipitate out as a salt. So it'd be a salt, not a pure metal. Choice D is off. So sure enough, A was the right answer, but I need to be thorough. Hopefully that's a mistake that you don't make too often. Okay, so again, we're doing a question based on figure 4-6. The voltage, if you recall, was 1.1 volts for the copper zinc half reaction. This question is asking for 5.5 volts, definitely more than 1.1. So intuition on this one, let's say you don't know anything about physics, you at least recognize 5.5 and 1.1. If in your mind you're saying there's a factor of 5, you're probably right. That's got to be somewhat important. But if you look at the answer choices, you still have to know some physics, parallel and series. So, little side note here, why do I do this? Why do I incorporate physics, GChem together? Why do I mix different materials, different subjects in all the chapters? Again, you're preparing for the MCAT. Two concerns when you go through this: if you tunnel vision just on one subject, you're knowing it in that context. You're not applying it to new situations. The MCAT is about applying it to new situations. You're never going to get a passage purely on electrochemistry. There's going to be other questions associated with it. So it's absolutely important that you mix together different questions. So every single chapter, I throw a few things from other material, maybe other sections in the same topic, or a totally different subject from bio or physics, or as it is in this case. So your job is to always be able to think on your feet. So 2 questions going on here. How many cells do I need? Questions 5 or 6, and are they hooked up in series or parallel? So let's go ahead and start with, mention that the 1.1 is the voltage. 5 times 1.1 is 5.5. So it's going to be 5 cells of some sort, and then series or parallel. In physics, you learned that resistors add in series, R1 plus R2 plus R3, etc., equals R equivalent. You learned that capacitors reciprocally add together. 1 over C equivalence equals 1 over C1 plus 1 over C2 plus 1 over C3, etc. But it's highly unlikely they ever went into what happens with batteries. For whatever reason, they just don't. So I want to address it here. Batteries, when you hook them up series head to head, or head to tail, head to tail, head to tail, and connect it like that, they add directly. So batteries in series add. That's why if you have a flashlight, a lot of times you'll hook up the batteries in that same fashion, head to tail, to increase the voltage out of the collective set of cells. In parallel, it's a little more complicated. You get a kind of a weighted average. Again, not sure why most physics classes don't cover this, but toss it to you here. So you have to have 5 hooked up in series. That part we get. And then the second part is, again, picking series over parallel. So they have to be series to add up 1.1 plus 1.1 plus 1.1, etc. So 5 cells hooked up in series. Again, physics mixed in with chemistry, you have to be able to do those things. So this question may seem out of place. It's meant to just keep you on your toes. The rules. Again, the rules are electrons flow from anode to cathode, anions migrate to the anode, cations migrate to cathode. So just want to take a moment to just sort of stop and emphasize why we have these rules. I mentioned they can be applied to any electrical system. So electrochemical cells, we're applying that here, but also electrophoresis or an electric field in a circuit. So let's consider electrophoresis. This is a generic picture. I've drawn the capacitor in a bizarre way where the plates are really far apart, but that's because when we do gel electrophoresis, the plates are far apart. If you've ever done one, they're approximately 6 inches apart. You're a pretty good distance. So we must realize what the key circuit elements are. So this is where physics is presenting its way into chemistry. The notation for a battery, you'll notice, is a short line and tall line at the upper part of the picture. Little anode, big cathode. In class, I go into a movie that I think, although every year I seem to be surprised that maybe this isn't so true, but I thought everybody saw the movie with Little Orphan Annie, and Annie is a little Annie, and in that character there's Daddy Warbucks, who's a fat cat. So we use a phrase from that movie: little anode, fat cathode, bigger cathode. Okay, whatever way you remember, it's fine. My way's dorky. I have no pride. I don't care whatsoever. If it helps me get a right answer, that's what I'm going to do. So we have the little anode, big cathode. The battery dictates what's going to happen in this system. It's the power supply. So the anode's going to push electrons, as we know, from anode to cathode. So electrons are going to flow in that direction, meaning when you look at the big plates, the parallel plates of the capacitor, the left one must be the cathode plate. The right one must be the anode plate, because the anode's always connected to the cathode. So electrons are going to flow from the anode to the cathode. So overall, the anode plate on the far right of the capacitor is going to send electrons to the cathode of the battery. The anode of the battery is going to send electrons to the cathode plate. This is going to put charges on each plate. This is where I want to just stop for a brief moment because this is where confusion suddenly kicks in for a lot of people. In physics, they emphasize that an anode is negative and cathode is positive, but they don't tell you they're talking specifically about a battery, the way we learn the battery and label the core charges. We typically label it the battery's cathode is positive, the battery's anode is negative. However, in this example, we're not interested in the battery's charge, we're interested in the plate charges because that's when it's going to cause the migration of whatever species we put in there, proteins, DNA strands, cations of some sort, anions of some sort, whatever we put in there. So you'll notice on the plates, the cathode is accruing a negative buildup, anode is accruing a positive buildup in the capacitor. So the reason I go so much into these rules, electrons flow anode to cathode, anions migrate to anode, cations migrate to cathode, is to avoid this discrepancy between whether we're talking about the charges on a battery or charges on a capacitor plate. It can get confusing. I'm going to ignore charges complete from this point and go back to the rules. If we were to place an anion solution, what way would it migrate? So an anion migrates to the anode because that's where the positive charges are built up on that plate. So rule number 2, anions migrate to the anode. Rule number 3, cations migrate to the cathode. If I put a cation in there, it's going to migrate to the cathode. Rather than worrying about what the charge is and honestly stressing yourself out, is it a battery, is it a capacitor, is it positive, is it negative, forget that and just follow the 3 rules. Electrons flow anode to cathode, anions migrate to the anode, cations migrate to the cathode. So again, those are the 3 rules. You'll notice then they applied first to electrochemical cells, then they just applied to an electrophoresis system or a circuit system, electric field. So if they were to ask you a question, which way does DNA migrate in electrophoresis? Your question, what is DNA? Well, because of the phosphate backbone, it's an anion. Anions migrate to the anode. Where will palladium cations get reduced? Could be a question from general chemistry. Well, palladium cations, it's a cation. Cations migrate to the cathode. They're going to go to the cathode to get reduced. Where do chlorides gather in an electrolytic cell? So again, another question from a different system, but you know chloride is an anion. Anions go to the anode. No matter what the system may be, electrophoresis, galvanic cell, electrolytic cell, it doesn't matter. The 3 rules apply. Know them fundamentally and try to simplify rather than complicate anything in this section. So this introduces the notion of what an electrochemical or electrolytic cell is. If you have a galvanic cell, as mentioned, the cathode gets bigger, the anode gets smaller. Eventually, though, you're going to run out of reactant, or it's going to get to so little reactant it reaches equilibrium and no more can go. So you have to be able to recharge it. And that's what figure 4-7 is trying to allude to. If you hook up 2 batteries in this fashion, anode to anode, cathode to cathode, technically you put them opposing one another. And so we have to decide which one is the more dominant one. So if the upper one were 4 volts and the lower one is 2 volts, 4 volts is a stronger battery than 2 volts, the 4-volt system is going to dominate the 2-volt system. In doing so then, I want to consider the upper battery because that's the one that's dictating the circuit. It is going to cause electrons to flow from the anode and it's going to force at the 2-volt site the poles to reverse. So the anode of the upper 4-volt battery is going to push electrons to what used to be the anode is now the cathode of the lower battery. And then the cathode in the upper voltage, the 4-volt system, is going to suck electrons that way. And so in essence, what we've done, I don't know if that's clear at this point, so let's figure out why we do it. Hopefully that'll help understand it. If your battery needs to be recharged, your cell phone runs out of voltage, your computer battery is dying, you need to recharge it, you plug it into a higher voltage source and it forces electrons to flow backwards from what the battery in your computer, battery in your cell phone, what they naturally want to do. So they want to flow in one direction. By applying a voltage, you force it the other way. So we are literally forcing the lower battery to run backwards. We're forcing the anode to turn into a cathode. We're forcing the cathode to turn into an anode. So an electrolytic cell is an electrochemical cell where the cell reaction is being forced to run backwards because of an applied voltage. So overall in this system, the electrons are flowing in a counterclockwise fashion because the upper voltage is higher than lower voltage, meaning the upper voltage is powering it, the lower voltage, in this case a 2 volt, is getting recharged. So think of the outlet you plug into as the upper one, your cell phone battery as the lower one, you're recharging it. So let's go ahead and apply it to a specific case. So electrolytic cells, they are an unfavorable chemical reaction. That's why delta G is now positive, E is negative. But we couple them with something that is more favorable. So what's absolutely critical, if the voltage of the reaction you're trying to run is normally positive 1.5, and then when run backwards it'd be a negative 1.5, the voltage source has to be greater than 1.5. The winning voltage, the bigger voltage, always has to be the outside applied voltage. I like to always look at the rules. Are the rules being followed? Electrons are in fact flowing from anode to cathode, check. Anions are migrating through the membrane to the anode, check. So cations must be built up on the cathode. So we'll eventually put that in there. So if the applied voltage, the voltage of the outside source, the outlet or the battery you hook it up to, is higher than the cell's voltage, then this electrolytic cell will work. Oxidation occurs at the anode, check. Reduction occurs at the cathode, check. Cations are going to migrate to the cathode in that solution. All the rules are being followed. So we have oxidation now where it used to show reduction. We have reduction where it used to show oxidation. Electrolytic cells are generally drawn, this is the standard convention how to drawn, emphasizing they are reversed. The poles reverse. What used to be an anode is now a cathode. What used to be a cathode is now an anode. So let's consider the zinc copper example from before. So before we showed a zinc anode and copper cathode in the natural galvanic cell. Now if I'm applying a voltage greater than 1.1, then I can force the copper, which used to be the cathode, to be the anode. I can force the zinc anode that used to exist into being a cathode. So you'll notice copper metal is now being reduced. So all that copper you plated out, you can now return back to solution. All the zinc that was being oxidized into zinc 2 plus can now be reduced back. You can plate out the zinc. So everything applies. Electrons are still flowing anode to cathode. Cations are still migrating to cathode. Anions are still migrating, in this case, across the membrane to the anode. So everything fits. So again, electron flow anode to cathode, check. Anions migrating to anode, check. And cations are migrating to cathode. So they're starting in, or the zinc 2 plus, they're going to migrate to the zinc and get reduced. So this covers everything for this. We're going to pick up part 4 as we go. Thanks for sticking around for this. I hope this helped. This is one of those subjects that I hope you took the time, stopped when you had to, paused when you needed to really pick up the rules. They really are simple. There's only 3 rules, and they apply to any of the systems. In the homework, you're going to run into something called concentration cells. You want to get homeostasis, you want to get equilibrium, you want equal concentration. If they seem confusing at first, just keep in mind, you want to move electrons in a way to get equal concentration of ions in solution, and they always flow from anode to cathode, so you can identify it that way. So good luck on homework. I'll see you in part 4.